Hi, and welcome to the last in our series of videos on thermodynamics and thermochemistry for AP and IB chemistry at Allen High School. In our last question, we're going to see entropy, free energy, equilibrium, and bond energies. Remember that one wacko thing where it's not final minus initial. No enthalpy interest. Oh, I lied to you. We're going to have to use enthalpy too. So this pretty much is everything we've talked about in this unit other than the calorimetry. So let's take a look. This would be in part A because it requires calculations. So this time it gives us the entropy change for the reaction above, and we're trying to find a standard molar entropy. So this is one of those sum of questions. So this is the reaction is going to be equal to the sum of products. So 1 times C2H6, that's our unknown. All right, minus our reactants, 1 times C2H2, which is 200.9, plus 2 times H2, which is 130.7. And include your units on here. I think that's pretty critical. That's going to be 229.6 joules per mole Kelvin. Right? Remember, delta S is typically in joules. That's S naught. That's our answer. It's not what we equal. That's what if I solve for X. Okay, now I want to get delta G. But in order to get delta G, I need to get delta H. So remember that delta G naught is equal to delta H naught minus T delta S naught. Now, absent of any information on delta G's of formation, I have no choice but to solve for delta H and use this formula. I don't know K, I don't know my delta G's of formation, and I don't have reactions for Hess's law, so this is really my only choice. So I first have to calculate delta H naught for the reaction, which is going to be 1 times again the C2H6, which is a minus 84.7. Now, remember, we're in the world of kilojoules per now at this point, minus 1 times my C2H2, which is 226.7. Be very careful transposing numbers down like that you don't flip them. Now, I do have 2 hydrogens, but they contribute diddly and squat to this. And so delta H naught is equal to minus 311.4 kilojoules. Now, to find delta G, I have to plug into this formula here. So delta G naught is my minus 311.4, which is exothermic and favorable, by the way, minus 298 times, now be careful because that's joules, this is kilojoules, so I have to convert this to 296. Okay, and it was positive, and that is also favorable, so this better be a negative value because I've got favorable and favorable, which is always spontaneous, and my math gave me 242.1 kilojoules for this reaction, which is for 1 mole of the C2H2, for 2 moles of H2, and for 1 mole of the ethane there. Now, it says to calculate the equilibrium constant for this. Well, if you don't remember, look at your formula chart. If you see on your formula chart, you see the formula that delta G naught is equal to minus RT ln of K. Now, R is, whoa, don't know what I did there. That's kind of fun, though. Whoa, there's our K. I'm sorry. I'm amusing myself late at night. Our R is in joules, and therefore the G needs to be, the delta G needs to be in joules as well. So minus 242,100 is equal to a minus 8.314 times 298 ln of K. Now, if you do that algebra, frankly, I think this is pretty silly to be calling this equilibrium, but hey, I'm not in charge here. AP is, and whoever wrote this question, we called this equilibrium when the value is 3 times 10 to the 42nd power. Seems pretty much like a stoichiometry to me. It's favorable. It's going pretty much 100% product, right? That's a pretty high K value to be calling that an equilibrium, but we still calculate them. So that would be your answer, and it's unitless. We don't talk about those units. Now, it says calculate the value of the triple bond energy in C2H2. So that is our hint that the structure of that is this. And if you remember a long, long time ago, before Christmas, you know, back when you didn't know all this abundance of chemistry, that this is an alkyne. And we add to that 2 HH bonds. I like to write them as molecular formulas. And we're going to get C2H6. I really like to write my structural formulas here, not molecular, I just misspoke. My structural formulas. And then I like to take and blast everything apart. And this is our one time that it is broken minus formed. And broken minus formed is going to be equal to minus 311.4 because we have the delta H of the reaction way up here. So this is more of an estimate, but it's going to get us a pretty good ballpark of what we're talking about. So the bonds that we break, that requires energy to break the bonds, is we would break 2 CH bonds and 1 C triple bond and 2 HH bonds. And we form 6 CH bonds and 1 CC bond. Now you can just plug in the values as is right there. I typically like to go through and cancel things. So I personally would cancel that and make that a 4. I net formed 4. But you don't have to do that if you don't want to. Okay? And now we just plug in the values that are given to us. So the 1 triple bond is our unknown, and the 2 HH bonds are given up in the chart as 436. Remember, this is the only time it's effectively reactants minus products because we always report bond energies as the energy required to break. And because of that, it forces us to do our math this way. So I netted 4. I'm stuck here. 4 times 414 plus 1 times 347 is equal to minus 311.4. And when we are done with that, we get 820 kilojoules per mole of triple bonds broken. So that's what the per mole means there. So that's the energy required to break that triple bond. Let me put a little box around it. That was our final answer for D. All right, that's it, kiddos. I just know you're just going to rock on this next test, and you're going to feel so good about yourself when all is said and done. So until then, this is, as always, signing off.